So my name is Luca Scalia, and my research name is development of a framework for coupled aerostructural optimization of new generation wings, and I'm supervised by Professor Cini and Professor Cavallaro. So the motivation is the commitment of the aerospace industry in reducing the impact of human flight. This is possible in several ways, for example, improving the aerodynamic efficiency of the airframe, which usually means increasing the aspect ratio of the wing, which in turn means increasing the aerostructural coupling, or including new concepts like truss-braced wings. In any case, when we tackle a new design idea, we cannot entirely rely on legacy experience because we need new design data from new tools and procedures that must be able to provide meaningful design data since the first design stages in order to avoid suboptimal design and the need to reiterate so additional design iteration to fix the design. So the objective is to craft a computational tool and procedure for high fidelity optimization and design of coupled aerostructural systems. The framework is modular and composed by different modules, the safety module, which is SU2, then the finite element code, which is an in-house code called Augusto. There's also a spline module to allow communication between the two. Speed and efficiency is achieved by means of the gradient-based optimization, in which the agile method and the algorithmic differentiation are used to compute the derivatives. And the code is designed in parallel in order to to deal with the large-scale industrial problems. Everything is kept modular so that the code maintenance is easier. Concerning the state of the art, the aerostructural optimization has attracted a lot of interest in the past 50 years. In the first works, like the one of AFTCA, reflected the limited computational power available. For example, the aerodynamics was done with the lifting line method. In the past 10-15 years, the high-fidelity models like RANS have been established. And then there was also a focus on increasing the speed of the sensitivity computation, for example, with the automatic differentiation, or dealing with more sophisticated optimization like optimization with considering mission profile, and also considering the problem of using multi-fidelity approaches. In my research, the majority of my work is on the design of the structural tool. The key contributions we identified are the development of the code as an adjoint structural solver, assist by algorithmic differentiation for size optimization, for which there's no another example for what I could see in the literature, and also to study extensively the performance of the code in terms of speed, scalability, memory, accuracy of the sensitivities, and some issues like partial AD recording. Now we'll focus on the structural problem. Actually, in the code we can. So the optimization is a mass minimization problem according to a set of design variables and considering some constraints related to 3 different analyses. So finite element analysis for stress evaluation, modal analysis, and linear buckling analysis. For each of them, we define a response and a constraint. For example, for the stress, we aggregate the stress through the Kressel-Myers-Tannhauser function. For the frequency, we want the distance between the two frequencies to be larger than the initial distance. And similarly, for the buckling, we want to increase the critical buckling load by a certain percentage. From the point of view of the computation of the gradients, the methodology is based on the adjoint method and the algorithmic differentiation. With the Codipack, which is the library we use for algorithmic differentiation, we record the function evaluation that computes the mass or one of the responses we are interested in. And then we compute the gradients in the following way. So for the mass, we need a single run of the reverse path to get all the gradient. For the stress, we solve the adjoint equations in 2 steps. First step, we get the adjoint state variables, and the second step, the gradient we are interested in. For the frequency and buckling constraint, we differentiate the expression of the responses, and the gradient of the eigenvalues that now we have in the expression are evaluated with a run of the reverse path. An issue we have to deal with is the fact that the code involves solving a linear system and or an eigenvalue problem. We never record the computational graph of the solution of these two problems because it is very, very memory consuming. And in general, it's not possible because the solution is handled by external libraries. So we stop the recording in correspondence of the solution of the two problems, and then to retrieve the information, we solve the adjoint statement related to the two problems, which are matrix operations, which so expressions which are much easier to be solved, so that can be solved much more efficiently. Then we made some tests, for example, on the wing, on the elastic benchmark of the University of Michigan. The wing is loaded vertically. It has 111 design variables. We consider 3 runs related to 3 optimization set, 3 constraint sets. The first one is a stress set in which we aggregate the stress on the areas of the wing. So we have 5 constraints simultaneously imposed. The second one is on frequency. So we keep the distance between the first two frequencies and between the second 2 frequencies equal, larger or equal than the initial distance. And then we want to increase by 15% the value of the first frequency. In the third case, we apply simultaneously the 8 constraints, having 8 in total. These were the results. So for the stress, we have reasonable results. So we have for the top and bottom skin, the thickness decreases moving toward the tip. For the frequency case, we had the minimum of the mass, and almost all the panels are at the lower bound. While in the mixed case is the stress constraint that drives the optimization. Indeed, the two masses are very similar, and also the thickness profile for the two skins. In the next steps, I'm finalizing my journal article, which is an application on the nonlinear case. Then we will join again the aerodynamics that I removed basically in the research of this year because I only focused on the structure. We will introduce a tracking method for detecting frequency swapping, and possibly the introduction of composites. Concerning the achievements, I took part twice in the Aerobest conference this year and 2 years ago. And before Christmas, I was doing the research stay in Germany, working on the sensitivity of the generalized eigenvalue problem. That's all. Thank you.